Hello and welcome to my presentation, First Principles Calculation of Power Conversion Efficiency for Photovoltaic Materials. In the face of climate change, we need more sources of renewable, clean energy. Solar energy is a promising and powerful option for this. However, it's currently limited by inefficiency, scarcity, and cost, among other factors. We can begin to solve this by performing high-throughput materials characterization to compute the efficiency of different materials and compare them to find the most effective ones. In this project, I learned how to do this through Quantum Espresso and Python code. First, we researched the theory behind computing the conversion efficiency of photovoltaics. Then I learned and practiced running DFT calculations through Quantum Espresso to determine the electronic and atomistic structures of a selection of materials. Once I found the basic properties I needed from DFT, I used Python to read in important information from the Quantum Espresso files and calculate the atomistic and electronic structures as well as dielectric and optical properties from these files. Then I compared my computed bandgaps with those in existing literature to evaluate the accuracy of my calculations and identify the most promising materials based on their bandgaps. Then, using my results, I would create a Python script to compute the conversion efficiency for the most promising materials, test and refine this package by running more calculations and comparing the results with those already published, and finally, applying the program to new materials to find which ones show promise as potential photovoltaic candidates. In the most simplified terms, solar cells create energy when photons from the sun hit the semiconductor and excite electrons. For a material with a given bandgap, only electrons with energy above that bandgap will be able to actually do this and create an electric current. Because the sun does not emit photons equally across all wavelengths, we have to figure out what wavelengths we can get the most energy from and find materials with that corresponding bandgap. The first way of finding the power conversion efficiency is the Shockley-Queisser or SQ limit. The maximum efficiency, N, is basically the ratio of the maximum power output by the semiconductor and the incident power from the sun. Maximum power can be computed by maximizing current density times voltage. Current density is computed with this formula here, which is then broken down into short circuit current density, JSC here, where AE is the absorptivity of the material and phi E is the photon flux density of the solar spectrum, which is the AM15G solar spectrum shown on the last slide. The recombination current density, JO, is calculated here, where h is Planck's constant, c is the speed of light, and T is the temperature of the solar cell. A more accurate calculation would be the spectroscopic limited maximum efficiency, or SLME limit, which takes into account material-specific factors such as the thickness of the material and its absorptivity, whereas the SQ limit only takes into account the bandgap. The SLME looks at both the absorptivity and the thickness of the material. To find the SLME efficiency, you replace absorptivity AE in the Shockley-Queisser equation with the absorptivity calculated here, where L is the thickness of the material and alpha E is the absorption coefficient from DFT calculations. SLME also takes into account non-radiative recombination for materials with indirect bandgaps with the FR equation here, where delta is the difference between the direct allowed and fundamental bandgaps, calculated here. If you have direct bandgaps, however, your delta is equal to 0 and you just have FR equals 1, just like in the Shockley-Queisser equation. When you look at the Shockley-Queisser limit versus the SLME limit, you can see that the Shockley-Queisser equation serves as a maximum efficiency for the actual efficiency of materials, which all fall below the SQ limit. There are ways to get above this limit, but for the sake of our purposes, we're just going to assume that the SQ limit serves as the absolute maximum for a material with any given bandgap. The first DFT calculations I ran through Quantum Espresso calculated the structural qualities of the materials. From these, I was able to visualize the atomic structures of the materials, such as in the image to the right. For my computational method, I used a DFT PBE functional with the PAW method. First, I ran V-serialized calculations to get structural information about each material. All materials used have a tetragonal unit cell. The CTA ratio for each material was compared in the table to evaluate the accuracy of the DFT PBE calculation. The results of these calculations were very similar to the structural qualities used in the reference paper, showing that the DFT-PBE method that I was using is plenty accurate for structural calculations. Here are the results after running the self-consistent, non-self-consistent, and density of states calculations. This figure is an example of the density of states data for one material. From this, we can calculate the band gap of the materials by finding the length of the line segments at zero energy when plotted with respect to the Fermi energy. In this example plot, the band gap is shown in the blue box. The results of my calculations are in the table to the right, along with two other methods of calculating the band gap. As you can tell, the method I am using, DFT-PBE, tends to underestimate the band gap. In contrast, the more complex GW calculation produces much higher results for the band gap that are closer to the real experimental values. After running the band structure calculations on Quantum Espresso, we created a Python script to read in the output of the band calculation and plot the band structure with respect to the Fermi level, as seen on the right. We used the high symmetry points seen on the image to the left, which was created using XChristen's software. The band gap was calculated from the plot by finding the difference between the lowest conductance band and the highest valence band of the material at the high symmetry points. As you can see, the direct band gap in blue between the valence and conductance band at the same high symmetry point is smaller than the indirect band gap in green between different high symmetry points. So the direct band gap was used instead of indirect. The band gaps calculated through the DFT-PBE method are much smaller than the band gaps in the reference. Although this is typical of the DFT method that I used, this causes issues for the calculation of the dielectric function and can cause serious issues with the accuracy of the final calculation of the conversion efficiency. In order to fix this in future work, we will need to redo the DFT-PBE calculations with a more accurate method instead, such as a hybrid exchange correlation functional. Using this more accurate functional, we will follow the same steps as we followed in this work, from the DFT calculations to comparison of structural and electronic properties to the calculation of conversion efficiency. Then we will expand this more accurate program to new materials. In summary, First Principles DFT is an efficient and accurate method for atomistic calculation. The unit cells and lattice parameters computed through DFT-PBE closely match with the experimental qualities of the respective materials. However, DFT-PBE did not produce accurate results for electronic properties, such as band gaps. Because the band gaps from DFT-PBE are far below the experimental values, a more accurate computational method is needed, such as DFT with hybrid functionals and advanced GW approach. I would like to extend sincerest thanks to everyone who helped me with this project in the O-REU program at Texas A&M. Thank you very much for listening and have a great day.